1 billion matter-antimatter pairs. 1 billion annihilations. And for every single one of them, nothing left behind. In the first 20 microseconds after the Big Bang, at temperatures of nearly 2 trillion degrees, the universe ran that experiment a billion times over, and a billion times the answer was the same. Total cancellation. Except once. One particle per billion pairs did not annihilate. It survived. That survivor, that single, statistically absurd leftover, is every star in the sky, every planet, every atom inside you. The entire observable universe is the rounding error from a catastrophe that should have been perfect. Here is the part physics cannot answer. Every equation we have says that survivor should not exist. The standard model predicts matter and antimatter in identical quantities. By that accounting, the universe should be a cold, featureless sea of photons and nothing else. No galaxies, no worlds, no witnesses. Instead, you are here, breathing, listening, made of the impossible leftover. In March of 2025, a detector at CERN recorded something that has never been observed in the history of science. A result so new it appears in no textbook on Earth. We will get to that. But first, understand what it would mean if we can never fully explain it, because the answer may be the most destabilizing idea the human mind has ever been asked to hold. Consider the size of that imbalance. Not a modest surplus, not 1 part in 10, or 1 part in 1,000, or 1 part in 1,000,000. 1 part in 1,000,000,000. Picture a stadium holding 2 billion people, every single one of them matched with an exact opposite, every pair primed to vanish in a flash of pure light. The lights go dark, the roar falls silent. When the brilliance fades, one person remains standing alone in an arena that an instant ago held a crowd beyond counting. That lone figure is the matter that became you. Everything you have ever touched, every word you have ever spoken, every person you have ever loved, is assembled from that one survivor in 1,000,000,000. The annihilation was almost perfect. Almost. And the entire reason you exist is that it was not quite perfect enough. This is the disturbing reality of our origin. We are not the main event. We are the residue. The universe was not built to make us. It was built to erase everything, and it very nearly succeeded. And a flaw too small to imagine is the only reason the lights came on at all. Which leads to the question that sits underneath every other question. Why is there something instead of nothing? It sounds like the kind of thing a child asks in the dark before sleep and forgets by morning. It is not a child's question. It is the oldest and the deepest question a conscious mind can ask. And for more than 300 years our finest thinkers have circled it without ever landing. Here is what most people get wrong. They assume existence requires no explanation. Of course there is something, they say, because here we all are. But the closer you look, the faster that assumption dissolves. The simplest possible condition, the state that needs no cause and no maintenance and no miracle, is not a universe. It is nothing at all. No space, no time, no law, no reason for anything to begin. And yet, somehow, here we are. The honest answer is that nobody fully knows why. Not the physicists, not the philosophers, not the equations. And that uncertainty is not a gap we are about to close. It may be a wall we will never cross. If you find a strange comfort in questions this vast, the kind that make the ceiling above your bed dissolve into open sky, do me a small favor and tap that like button and subscribe. It genuinely helps this channel grow, and it lets me keep making these long, slow journeys into the deep questions for you. There is nothing you need to solve tonight. There is nothing you need to remember. Make yourself warm and comfortable. Let your shoulders soften, and let the sheer weight of this question carry you wherever it wants to go. We are about to spend the next few hours inside the largest question ever asked. Let's begin. The question feels modern. It feels like something assembled in the 20th century. in the cold light of particle accelerators and the chalk dust of lecture halls. It is not. The question is old. It is older than every instrument we have ever built to chase it, older than the word physics, older than the very idea that the universe had a beginning we could measure. Long before anyone could weigh an atom or read the temperature of empty space, a single human being sat down and wrote the question out in plain language. And once it was written, it could never quite be unwritten again. To feel the full strangeness of existence, it helps to begin not with the Big Bang, but with a man at a writing desk. The year is 1714. The man is Gottfried Wilhelm Leibniz, born in 1646, now near the end of a long life that would close just 2 years later. He is one of the great minds of his age, a man who has spent decades turning the machinery of the world over in his hands, looking for the gears beneath everything. In a short and dense little work we now call the Monadology, he sets down a single line that would outlive almost everything else he ever wrote. The first question which should rightly be asked, he writes, is this: why is there something rather than nothing? Read it slowly. It looks almost too plain to be dangerous. There are no difficult words in it, no equations, nothing that requires a degree to follow. A child could ask it, and children often do, somewhere in the dark before sleep. Yet that one sentence has the strange property of getting larger the longer you look at it. It is not a riddle with a clever trick at the center. It is not a puzzle waiting for the right key. It is a question that seems to dissolve the flaw beneath every answer you could possibly offer it. Leibniz did not ask it to leave it hanging. He was not a man who enjoyed open wounds in his logic. He believed with total seriousness that nothing in this world is true or real without a sufficient reason, or why that explains it fully. A stone rolls because something pushed it. A fact is true because some deeper fact makes it true. Follow any chain of reasons backward, and each link must hang from another link behind it. For Leibniz, this was not a suggestion. It was a law as binding as gravity. Nothing simply is. Everything is because of something. And here the law turns on its maker. If everything that exists needs a reason outside itself, then the whole of existence taken altogether must also need a reason. But that reason cannot sit inside the universe, because the universe is exactly the thing we are trying to explain. So Leibniz reached for something that could stop the endless backward fall. He reasoned that there had to be a being whose explanation lay entirely within itself. A being that did not borrow its existence from anything earlier or anything outside. A necessary being, one that could not fail to exist, which he named God. It is a beautiful move, and for many people it is enough. But notice what it actually does. It does not close the question, it relocates it, because the moment you name a necessary being as the reason for everything, a quiet voice asks the obvious next thing. And why is there that being, rather than nothing at all? Leibniz answers that this being contains its own reason, that its very nature is to exist. Perhaps. But you can feel the question pressing against that answer like water against a door. We have not escaped the problem. We have only pushed it one room deeper into the house and shut the door behind us. This is the first thing you must understand about the question we are inside tonight. Its difficulty is not technical. The trouble is not that the mathematics is too hard or that the words are too tangled. The trouble is that the question seems to swallow every answer whole. Offer it a God, and it asks why that God. Offer it a law of physics, and it asks why that law. Offer it a quantum field humming in the dark, and it asks, with the same flat patience, why that field and not nothing. Every floor you build, it asks what holds the floor, and to see why, you have to take seriously the smallest and strangest word in the whole sentence. Nothing. We say it constantly. We treat it as ordinary, as a synonym for empty, for absence, for the bottom of a drawer. But the nothing Leibniz meant is not an empty room. An empty room is full of air, full of space, full of the silent rules that govern that space. His nothing is not the absence of objects. It is the absence of absence itself. No matter, and no space for matter to be missing from, no time, and no instant in which the missing could be noticed. Not a darkness, because darkness is a thing that light could enter. Not even a silence, because silence is something a sound could break. Try to picture it, and you will fail, and the failing is the point. Your mind keeps smuggling something into the frame. A black void, a grey fog, a waiting stage with the lights turned down, but every one of those images is already something. The void has dimensions, the fog has particles, the stage has a floor. The true nothing has none of these, not because we have not looked carefully enough, but because there would be nothing there to look at, and no one there to look. This is the abyss Leibniz set at the edge of his question, and against that abyss, the plain fact that you are here, breathing warm beneath your blankets, becomes almost unbearable to explain. You might expect a question that radical to burn out quickly, to be answered or abandoned within a generation. It did the opposite. It went underground and grew. It passed from hand to hand across 2 centuries, surviving wars and revolutions and the slow rise of the machines that would eventually let us measure the heat of the early cosmos. And when it surfaced again, fully and forcefully, it was in the mouth of one of the most difficult thinkers of the modern age. The year is 1929. The place is the University of Freiburg in Germany. The man is the philosopher Martin Heidegger, and he is standing before an audience to deliver a lecture that he titled, simply, "What is Metaphysics?" Near its heart he poses Leibniz's old question again, sharpened to a finer edge. Why are there beings at all, he asks, and why not rather nothing? Then he does something that should stop you cold. He calls this the fundamental question of metaphysics, not one question among many, not an interesting puzzle for a quiet afternoon. The fundamental one. The question beneath philosophy itself, the question from which every other question is only a branch. Consider what that claim is really saying. Heidegger is not telling us that this is the hardest question to answer. He is telling us that it is the first question, the one that has to be faced before any other inquiry can even find its footing. Before you ask what something is, before you ask how it works or where it came from or what it means, there is the older and more terrible fact that it is at all. We spend our entire lives studying the contents of existence. We almost never turn to look at existence itself, the bare brute fact that there is a something here to study. Heidegger wanted that fact dragged into the light. He wanted us to feel the strangeness we have all agreed quietly to ignore, and he was not alone in feeling it. Around the same stretch of the early 20th century, another philosopher had circled the very same mystery from a completely different direction, and arrived at a conclusion just as unsettling. His name was Ludwig Wittgenstein, and in his early masterwork, the Tractatus, he drew a strange and careful line. The mystery, he suggested, is not how the world is. It is not the arrangement of things, the laws they obey, the patterns we can chart and predict. All of that, in principle, can be described. What cannot be described, what slips entirely outside the reach of every sentence we could form, is the simple fact that the world exists at all. Not how it is. That it is. This, Wittgenstein said, is the mystical. Consider what that single word was doing. Wittgenstein was no mystic in the ordinary sense. He was a logician, a man who spent his life trying to pin language to its hardest and clearest edges, to say only what could be said with precision, and to fall silent about everything else. And yet here, at the very boundary of his careful system, he met something he could not dissolve into logic. The existence of the world, not its contents which logic could chart and order, but its sheer presence, which logic could only gesture toward before going quiet. For a thinker so devoted to clarity, this was a remarkable confession. The most important fact about reality, he was admitting, is the one fact that no sentence can ever hold. This is the strange inheritance the question carried down the centuries, from Leibniz at his writing desk in 1714, to Heidegger before his students in 1929. To Wittgenstein in his spare and difficult prose, the mystery was passed from hand to hand like a sealed box that no one could open. Each thinker felt its weight in the palm. None of them found the key, and for almost all of that long stretch, the question seemed to belong entirely to philosophy and to theology. To be a matter for argument and for faith, never for measurement. It was not a puzzle you could carry into a laboratory. It was not a riddle that any instrument could touch. Some of the most powerful minds in history simply refused to answer it at all. In 1948, the British philosopher Bertrand Russell, in a famous radio debate, offered what may be the most defiant reply ever given to the question. The universe, he said, is just there, and that is all. No cause, no reason, no deeper why beneath the why. It is a brute fact, a thing that simply is. And the demand for an explanation was, in his view, a demand that reality was under no obligation to satisfy. This is not an evasion, it is a position, and a serious one. The hunger for a reason lives in us. The cosmos never promised to feed it. Decades later, the physicist Sean Carroll would echo that same calm refusal in words that are almost unsettling in their composure. The universe, he argues, simply is, without ultimate cause and without ultimate explanation. The question feels desperately urgent to the creatures asking it. The universe itself appears entirely indifferent to the asking, and perhaps that indifference is the most honest answer we have. Not a solution. A shrug written in the language of physics. Yet others felt the opposite pull entirely. The philosopher Jean-Paul Sartre, circling the same dark centre, arrived at something far stranger than a shrug. Perfect nothingness, he suggested, would annihilate itself. Absolute non-being, in his vision, is not a stable and restful blank. It is something inherently unsteady, something that carries within itself the seed of its own undoing. And notice how close that intuition sits to an idea that would later rise, not from a philosopher's armchair, but from the cold mathematics of the very small. The thought that nothing, true and total nothing, might be the one condition this universe is simply unable to hold. You have felt this question yourself, even if you never once put it into words. It arrives most often in the dark, in the quiet minutes before sleep, when the day has fallen away and the mind begins to drift past its usual concerns. The thought surfaces without warning. There could have been nothing at all. No stars, no earth, no breath moving in and out of your chest. No you to notice the absence, because absence would have been all there ever was. And then, just as quickly, the mind flinches away from it, because the thought has no floor to stand on. This is not a failure of intelligence. It is the natural reflex of a mind brushing against the one question it was never built to hold. And this is the turn that changes the entire shape of the story. For 200 years the question had no instrument behind it. Then, slowly and unevenly across the 20th century, physics began to do something that no philosopher had ever managed. It began to make the question measurable. The mystery did not shrink. If anything, it deepened. But it changed its very character. It stopped being only a question of why there is something, and became in part a question of how, and of how much, and of when. The box was still sealed, but for the first time we had tools that could weigh it. Consider one of the most disorienting ideas to come out of modern cosmology, the notion that the total energy of the entire universe might be exactly zero. It sounds absurd on its face. The cosmos is flooded with energy. It is locked into every star, every atom, every particle of light streaming across the dark, an unimaginable abundance, and all of it real, and all of it counted as positive. But there is another column in the ledger. Gravity. The gravitational attraction binding all that matter together represents a vast reservoir of negative energy, the energy of pulling inward, and when you finally add the two columns together, the positive and the negative, something extraordinary appears on the page. In a universe that is spatially flat, and our measurements of the most ancient light in the cosmos tell us that ours is flat to an exquisite precision, the two sides cancel, Not approximately. Exactly. The grand sum of everything comes to nothing. Sit with what that quietly implies. If the universe holds zero net energy, then calling it into being did not require borrowing some colossal quantity of energy from beyond. It did not demand a vast input that would itself cry out for explanation. The cosmos in this picture is not a brazen violation of the conservation of energy. It is a balance sheet that settles to zero. The matter and the light standing on one side, the deep pull of gravity standing on the other, the total, a perfect and silent nothing. Something from nothing stops being a logical scandal and becomes, at least in principle, an even balance. And just as physics seemed to be closing its hand around an answer, it uncovered a discrepancy so vast that it has earned the title of the worst prediction in the history of science. Here is the problem. When physicists use their finest theory, quantum field theory, to calculate the energy that ought to be present in empty space, in the pure vacuum with every particle of matter stripped away, they arrive at a staggering number. When astronomers measure the actual energy of that same empty space, by watching the precise way the universe expands, they arrive at a number that is real and positive and almost incomprehensibly small. The gap between the prediction and the measurement is not a factor of 10. It is not a factor of 1,000, or 1,000,000, or 1,000,000,000. The theory overshoots reality by a factor of 10 to the 120th power. That is a 1 followed by 120 zeros. To feel the size of that error, imagine carefully estimating the number of grains of sand on a single beach, and being wrong, not by a handful, but by more grains than there are atoms in every beach, every desert, every ocean floor, every planet, and every star in the entire observable universe, and then being wrong by that same impossible margin again, many times over. That is not a small misunderstanding at the edges of our knowledge. That is our finest theory of the emptiness, failing by the widest margin any theory has ever failed. Think for a moment about what these two facts mean when you set them side by side. On one hand, the universe may cost nothing at all, a perfect zero, a thing that needs no vast power to begin. On the other hand, the very emptiness it begins from is so poorly understood that our equations describe it with the least accurate prediction ever produced by a working science. We have a theory that says the cosmos was free, and we have a theory of the void that is wrong by a number too large to write down. Both of these are our finest knowledge. Both of them are standing on the same trembling ground. So here is where 200 years of patient asking has finally delivered us. We can write the question in the precise language of mathematics now. We can balance the energy of the entire cosmos and watch it settle to zero. We can reach into the emptiness of space and find it humming with an energy that our most powerful theory misjudges by the largest margin in the history of human thought. The question that Leibniz first set down in 1714 has not been answered. It has only grown teeth. Because the harder we have looked into the nothing, the clearer one deeply disturbing possibility has become. That nothing, true and absolute nothing, the clean and total absence the word seems to promise, may be the single state that this universe will never, under any circumstance, permit to exist. There is a place where this question stops being philosophy and becomes physics. It is a cold room, a quiet desk, and a single line of mathematics that should never have worked. If nothing is forbidden, if the void itself is unstable, then the something we are made of must have a history of how it arrived, and a history of how, against every reasonable expectation, it managed to survive at all. That history does not begin in a cathedral or a lecture hall. It begins with one man and an equation he did not entirely trust. In January of 1928, in Cambridge, England, a physicist named Paul Dirac was trying to do something the greatest minds of his generation had failed to do. He was attempting to write a single equation that described the electron in a way that obeyed both of the deepest theories then known. One was quantum mechanics, the strange new science of the very small. The other was relativity, the law of space and time and motion. The two refused to agree with each other. Dirac was searching for the sentence written in mathematics that would force them into harmony. Then he found it. The equation was elegant, compact, and astonishingly accurate. It predicted the behavior of the electron to a precision no one had ever reached before, but the equation carried a second answer hidden inside it. Not a mistake, not a rounding error to be quietly swept aside. A second, complete, mathematically perfect solution that described a particle identical to the electron in every way but one. It carried the opposite electric charge. This was the disturbing part. Dirac had not set out to invent a new kind of matter. He had set out only to describe the particle we already knew, but the mathematics would not let him stop there. The equation insisted, with the cold certainty that only mathematics can carry, that for the electron to exist as described, a mirror twin had to exist alongside it. A particle with the same mass, the same spin, and a charge flipped exactly backward. He called it the anti-electron. We now call its entire family antimatter. Consider what this means. A man sat alone with a piece of paper, moved symbols according to rules, and the symbols told him that a hidden category of matter must exist throughout the universe. Not because anyone had ever seen it, not because any experiment had demanded it, but because the equation, taken seriously, would accept no other answer. This was the first time in human history that pure mathematics predicted a new form of physical reality before a single instrument had ever detected it. Dirac would receive the Nobel Prize in Physics in 1933. The prediction was that profound. For 4 years, the anti-electron remained only a symbol on a page. Many physicists, including some of the most respected figures of the age, suspected it was a flaw in the theory, a phantom that nature would politely decline to produce. They were wrong. In 1932, at the California Institute of Technology, a young physicist named Carl Anderson was doing work that had nothing to do with Dirac at all. He was photographing cosmic rays, the high-energy particles that rain down upon the Earth from deep space, as they passed through a device called a cloud chamber. Inside that chamber, a charged particle leaves behind a thin trail of condensation, a visible streak, like the vapor line drawn across the sky by a distant aeroplane. By placing the chamber inside a magnetic field, Anderson could watch those trails bend. The direction of the bend revealed the particle's charge. One day, a track appeared that curved the wrong way. It bent in the direction that only a positive charge could explain. At first, that seemed unremarkable, because positively charged particles were already well known. But this track was too thin, too delicate, too easily bent by the field. A proton, the familiar positive particle, was far too heavy to leave a trail so faint. This particle was light as an electron, and yet it carried the charge of an electron's exact opposite. Anderson, at that moment, did not even know about Dirac's prediction. He had simply photographed the thing the equation had promised 4 years before. It was the anti-electron. Anderson named it the positron, and with that single curving streak of vapor, antimatter stepped out of the mathematics and into the physical world. The shadow twin was real. The universe truly did contain a mirror version of its most common particle, and that fact, beautiful as it was, carried a quiet and terrible implication that would take the rest of the century to fully absorb. Here is the problem. When a particle of matter meets its antimatter twin, they do not coexist. They do not bounce apart and go their separate ways. They annihilate. The two of them vanish completely. Their entire mass converted into a flash of pure energy, into light. This is not a rare or violent exception to the laws of physics. It is the law, working exactly as written. Matter and antimatter are perfect opposites, and when perfect opposites meet, they erase one another, leaving behind nothing but radiation streaming outward at the speed of light. Now carry that single fact all the way back to the beginning of everything. Carry it back to the first moments after the Big Bang, when the universe was not stars and galaxies and quiet, empty space, but a furnace beyond all imagining. In the first 20 to 30 millionths of a second of existence, the entire cosmos was a seething plasma of the most fundamental particles, quarks and gluons, crushed together at a temperature of roughly 1.85 trillion degrees. That is a number the human mind cannot truly hold. It is far hotter than the core of any star that has ever burned. It is hotter than anything that exists anywhere in the universe today. In that inferno, matter and antimatter were being created endlessly, in perfectly matched pairs. For every particle, an antiparticle. For every electron, a positron. For every quark, an antiquark. They poured into existence together, and an instant later met and annihilated together, flashing back into the light from which they had come. Creation and destruction, balanced so precisely that the whole universe should have ended as nothing more than a fading glow of radiation. A cosmos made entirely of light, not a single atom of solid matter anywhere within it. If that balance had been perfect, you would not exist. Nothing would. There would be no Earth, no sun, no galaxies, no chemistry, no minds to wonder why. There would only be cooling light, spreading thinner and colder across an empty and eternal dark. The honest expectation, written directly into the symmetry of the physics, is annihilation. Total. Complete. Final. The universe, obeying its own rules, should have cancelled itself out in the first fraction of its first second. But it did not. And the reason it did not is the most astonishing rounding error in the entire history of reality. For reasons we will spend the rest of this journey trying to understand, the balance was not quite perfect. For every billion antiparticles, there were not exactly a billion particles of matter waiting to be destroyed. There were 1,000,000,001. A single extra particle of matter for every billion matched pairs that flashed into oblivion. Consider what that means for you, lying here in the dark. Picture 1,000,000,000 particles of matter, and beside each one its perfect opposite, 1,000,000,000 antiparticles, set against each other in the first instant of time. They collide, they annihilate, they flash away in pairs, 1,000,000,000 brilliant erasures, until almost nothing of that original matter is left. Almost. One particle in every billion remains standing alone, with no twin surviving to destroy it. That solitary leftover, multiplied across the whole of the infant cosmos, is everything. It is all the matter there will ever be. Measurements of the oldest light in the universe, the faint afterglow left over from the Big Bang itself, have pinned this ratio down with extraordinary precision. They agree, to within 1%, with what the formation of the very first atomic nuclei independently predicts. The number is not a guess. It is not a convenient story. It is one of the most carefully measured quantities in all of science. One survivor in 1,000,000,000. That is the precise margin by which this universe chose to exist, rather than dissolve back into radiation. Every atom in your body is one of those survivors. Every atom in this room, in the screen you may be slowly drifting away from, in the quiet air moving in and out of your lungs, is a particle that should have been annihilated and somehow was not. You are not made of the universe's abundance. You are made of its leftovers, the single, lonely fraction that escaped the great erasure, when nearly everything else around it was turned to light and lost. And here is where the wonder curdles into something stranger. Because annihilation, by every law we understand, should have been fair. The early universe had no reason to prefer matter over antimatter. The equations that describe particle creation treat the two as mirror images, equal partners, indistinguishable in almost every way that matters. A perfectly symmetric universe, born from perfectly symmetric laws, has no mechanism to produce 1,000,000,001 of one kind and only 1,000,000,000 of the other. The symmetry should have held. The annihilation should have been complete. We should not be here. Yet we are. And so the survival of that one particle in 1,000,000,000 is not a small detail. It is the central crime scene of existence. Something, in the first instance of time, tipped the scales. Something allowed a little more matter to be made than antimatter. or allowed a little more antimatter to be destroyed than matter. Something broke the perfect mirror, and the search for that something, for the precise law of nature that decided you would be permitted to exist, would lead physicists into the strangest and most unsettling territory that the 20th century had to offer. But before we follow that search, we must understand exactly what was lost. We must understand what annihilation truly means. When a particle of matter meets its antimatter twin, they do not collide and shatter. They do not break into smaller pieces. They cease to exist entirely, both of them, in the same instant, converting the whole of their mass into pure radiation. Nothing physical remains. No fragment, no ash, no residue. Only light, racing outward, carrying away every trace of energy the two particles ever held. This is the most complete transformation known to physics. Not a partial conversion like the burning of wood or the splitting of an atom, but a total one, in which the entire mass becomes energy and the matter simply vanishes from existence. This is not a theoretical curiosity. We have made antimatter in our laboratories, and we have watched it disappear exactly as the equations promised, leaving only a pulse of radiation and an empty space where two particles used to be. The ghost that Paul Dirac conjured out of pure mathematics turned out to be entirely real. In the first moments of the universe, this same process did not unfold a few particles at a time. It happened everywhere, all at once, across the whole of creation. To understand the scale of it, picture the early universe not as a place, but as a furnace. In the first 20 to 30 millionths of a second after the beginning, everything that exists was compressed into a seething sea of the most fundamental particles, hotter than anything the cosmos has held since. The temperature stood above 1.85 trillion Kelvin. At that heat, matter as we know it could not survive. Protons and neutrons could not form. There was only a plasma of quarks and gluons, the smallest pieces of reality, moving freely in a fog so dense and so violently hot that the ordinary rules of matter did not yet apply. No solid thing could exist in such a place. A diamond, a mountain, a star, all of them would have been torn instantly into their smallest parts and swept back into the formless glow. Then the universe cooled, not slowly, by any human measure, but in less time than it takes a single thought to cross your mind. As the temperature fell through a critical threshold, the quarks could no longer roam free. They bound together into protons and neutrons and their antimatter counterparts, and the great annihilation began in earnest. Every particle that found its mirror twin vanished into light. The sky was not dark in that instant. It blazed. The whole young cosmos became a furnace of mutual destruction, matter and antimatter erasing one another everywhere at once, flooding all of space with radiation. Here is the part that should not have left anything behind. The annihilation was very nearly perfect. For every billion particles of antimatter, there were 1,000,000,001 particles of matter. The billion matched pairs found each other and disappeared. The single leftover particle, the one with no partner to cancel it out, survived. That lonely remainder is everything. Not most of everything, everything. Every atom in every star, every grain of dust adrift between the galaxies, every molecule of water and iron and carbon in your body descends from that one survivor in 1,000,000,000. To feel how slender that margin truly is, picture a great crowd of 2 billion people, evenly split, 1 billion standing on each side, every person matched against an exact opposite. Now add a single extra person to one side. Let the matched billions on both sides reach across and vanish, every pair erasing itself in a flash. That one unmatched person, left standing alone in the emptied stadium, is the entire visible universe. The cold light of that ancient annihilation is still here, all around us. For every single atom of ordinary matter in the universe, the sky still carries more than 1 billion particles of light, the faint and frozen afterglow of all that destruction. We measure that ratio today with extraordinary precision. It agrees with predictions made about the first minutes of the universe to within 1%. The number is not a guess. Roughly 6 particles of matter survived for every 10 billion particles of light that fill the cosmos. Change that one figure even a little, and the universe that follows looks nothing like ours. It is among the most carefully verified numbers in all of science. Consider what this means for your own body. The iron in your blood, the calcium in your bones, the carbon threaded through every living cell. All of it is the leftover remainder of a near-total extinction. You are not made of ordinary stuff that merely happened to be lying around. You are made of survivors. Not metaphorically. Atom by atom, the proof is in your hand. Each particle you carry endured a moment when the universe tried to cancel itself out completely, when annihilation came for nearly everything, and a vanishingly thin sliver of matter slipped through. Had the ratio been exactly even, the annihilation would have been total. The universe would have become an ocean of light and nothing else. No galaxies, no stars, no planets, no chemistry, no you. This is the strange intimacy of the question. The reason there is something rather than nothing is, quite literally, written into the matter of your hand. You can lift your fingers and look at them, and know that every particle within them is a survivor of an event so violent and so nearly complete that its very incompleteness is the only reason you can make the gesture at all. It is a fact that sits in the body rather than the mind, quieter and heavier than fear. And yet, by every law we have ever written down, that survival should have been impossible. The equations contain no instruction that favors matter over antimatter. They are even-handed. A theory that creates a particle creates its antiparticle in the same breath, in equal number, with equal likelihood. Run the mathematics forward from a perfectly balanced beginning, and you arrive at a perfectly balanced end. You arrive at total annihilation. You arrive at light and nothing else. It predicts emptiness. It predicts radiation streaming forever through a cosmos, with no one inside it to measure the streaming. The mathematics that has never once failed an experiment predicts a universe in which you cannot exist. So something must have tipped the scale. Either the universe was born already lopsided, carrying its excess of matter from the very first instant for no reason anyone can name, or some process in those opening fractions of a second manufactured the imbalance from a perfectly even start. The first answer explains nothing. It only pushes the mystery back to the beginning and abandons it there. The second answer is far more demanding. It insists that the laws of nature themselves must hide a faint and deliberate preference for matter, woven into reality and waiting to be found. For that to be true, the universe would have to break one of its most cherished symmetries, a balance so fundamental that physicists had long assumed it could never fail. The notion that nature might quietly cheat sounded less like physics and more like heresy. Most expected the books to balance perfectly. They were wrong. Not slightly wrong. Wrong in a way that would shake the foundations of the field. The place where the perfect mirror was first caught cracking was neither a cosmic furnace nor a distant star. It was a modest laboratory on Long Island, in the middle of the 1960s, where two physicists watching one of the most fragile particles ever observed noticed a whisper of difference that should not have been there. The laboratory sat on the flat coastal land of Long Island, and the year was 1964. The two physicists were named James Cronin and Val Fitch. Neither man had set out to wound the universe. They were studying one of the strangest objects known to physics, a particle called the neutral kaon, a fleeting flicker of matter that holds together for only the smallest sliver of an instant before it comes apart. The kaon is not something you can hold in your hand. It is not something you can set on a shelf and return to later. It is born in the violence of a collision. It drifts a short distance through the detectors, and then it dissolves into lighter particles, leaving behind nothing but the faint recorded trace of its passing. To understand why two careful men watching such a particle would end up shaking the foundations of their entire field, you have to understand what they believed they would see, not what they hoped to see, what they were certain of. Physicists of that era held an assumption so deep that most of them never thought to question it, an assumption about symmetry. The universe, they believed, did not play favorites. It obeyed a perfect mirror. That mirror had a name, and the idea behind it was elegant and simple. Imagine taking any process in nature and performing two operations on it at once. First, replace every particle with its antiparticle, every speck of matter exchanged for its opposite twin. Then reflect the entire process in a mirror, swapping left for right as cleanly as a reflection lying still on the surface of water. If the universe were truly even-handed, the result would be indistinguishable from the original. A process and its mirrored antimatter twin would unfold in exactly the same way, governed by exactly the same laws. The cosmos would have no way to tell the two apart. This was not a casual guess. It was a cornerstone. The symmetry felt as solid as the floor beneath their feet, as obvious as the conviction that the laws of physics should not care whether you are built from matter or from antimatter, whether you are watching the world directly or through a pane of glass. To suggest that nature might secretly prefer one over the other was to suggest something deeply uncomfortable. It was to suggest that the universe kept a hidden bias, a thumb pressed quietly down on the scale. Almost no one believed such a thing could be true. And then, Cronin and Fitch watched their kaons fall apart. The neutral kaon belongs to a family of particles called mesons, each one assembled from a quark and an antiquark bound together, matter and antimatter locked inside the same fragile object. These particles were expected to decay in a particular way, a way that honored the perfect mirror. The overwhelming majority of them did exactly that. But a tiny fraction, a mere whisper among the multitude, decayed down a different path. They decayed in the way the mirror forbade. It was not supposed to be possible. According to the symmetry that nearly every physicist trusted, it simply could not happen. And yet there it was, recorded again and again, stubborn and patient, refusing to vanish no matter how long they looked. The first instinct of any good scientist faced with an impossible result is to assume that the result is a mistake. Cronin and Fitch were good scientists. They did not rush to announce a revolution. They went hunting for the error instead. They examined their equipment. They interrogated their own assumptions. They considered every ordinary explanation that might account for the handful of forbidden decays, every stray effect, every contamination, every quiet flaw in the apparatus that could counterfeit a miracle. One by one, the mundane explanations fell away. The effect was not an artifact. It was not a glitch. It was real. The mirror was cracked. This is the quiet, devastating reality of what they had found. The universe is not perfectly even-handed. It does not treat matter and antimatter as flawless reflections of one another. Buried in the behavior of these delicate particles was a faint and undeniable preference, a tiny asymmetry stitched into the laws of nature themselves. Matter and antimatter are not identical twins standing on opposite sides of the glass. They are almost identical. Almost. But not quite. And that narrow gap between almost and exactly turns out to be one of the most consequential differences in all of science. The phenomenon earned a name. It is called the violation of charge and parity symmetry, or more simply, CP violation. The discovery was so important, so unexpected, and so far-reaching that it would carry both men to the highest honor their profession can bestow. In 1980, 16 years after they first watched their kaons betray the mirror, James Cronin and Val Fitch received the Nobel Prize in Physics. The award recognized a single slender fact, a fact that fits into one short sentence, yet reshapes everything around it. The universe, at its deepest level, is not symmetric. It leans. Ever so slightly, it leans toward matter. Consider what this means in the context of the question that has carried us this far. We began with a cosmos that should have erased itself completely, matter and antimatter annihilating one another in the first microseconds, leaving behind nothing but a sea of light. We asked how a single particle in a billion managed to escape that great cancellation, and here, in a modest laboratory on a stretch of coastal land, was the first physical clue that such an escape was even thinkable. If matter and antimatter behave in subtly different ways, then perhaps the infant universe could have tipped, just barely, in matter's favour. Perhaps the books never had to balance after all. Perhaps the imbalance was not an accident but a consequence, written quietly into the rules from the very beginning. It was the first crack of light through a door that had seemed sealed shut. But a crack of light is not a sunrise. The asymmetry that Cronin and Fitch uncovered was real, and it was profound, and it pointed in precisely the right direction. Yet it was also achingly, almost insultingly small. The difference they measured was a faint thing, a rare exception lost among countless ordinary decays. The question that followed immediately was whether such a delicate effect, multiplied across the whole of the early universe, could possibly account for everything that now exists, for every galaxy and every star, for every grain of sand and every drop of rain, for every atom in every living body that has ever drawn breath. The honest answer, even now, is troubling, because finding a single broken symmetry is not the same as explaining an entire universe full of matter. It is one ingredient, no more. A discovery like this raises as many questions as it settles. What exactly would have to be true in those first searing moments for a faint preference glimpsed in particle physics to harden into the lopsided cosmos we inhabit? What conditions would the young universe have needed to satisfy? How many separate ingredients does the recipe for existence actually require? The crack in the mirror told us that the universe could lean. It did not tell us how the universe came to lean so completely that nothing remained to cancel us out. That answer would arrive 3 years later, and it would come not from a laboratory bench on Long Island, but from the mind of a single physicist working quietly inside a country that would have greatly preferred he stay silent. His name was Andrei Sakharov. The year was 1967. The place was the Soviet Union, a nation that prized its physicists for the weapons they could build and grew uneasy whenever those same minds drifted toward questions of conscience. Sakharov had spent years near the center of his country's most secret work. Now he turned toward a problem with no military use at all. He wanted to know why the universe contained anything whatsoever. He had studied what Cronin and Fitch found 3 years earlier on Long Island. He understood the cracked mirror. The laws of physics did, ever so faintly, favor one version of reality over its reflection. But Sakharov saw something the experiment alone could not say. He saw that one broken symmetry by itself was not enough. It was necessary. It was not sufficient. To bend a perfectly balanced cosmos into a lopsided one, you would need not a single special condition but 3, and all 3 would have to hold at once, in the same instant, in the same cooling fire of the early universe. This is the quiet achievement that would one day carry his name, the 3 Sakharov conditions, a recipe for existence, set down by one man, in a country that would later try to silence him for reasons that had nothing to do with physics. The first condition was the strangest. It demanded that the total quantity of matter in the universe not be a fixed and protected number. Somewhere, somehow, in those first fractions of a second, a process had to exist that could manufacture a genuine surplus of matter where the books had previously balanced. Physicists call the bookkeeping quantity baryon number. Sakharov's first rule said plainly that baryon number must be violable. Not conserved forever, not locked. The universe had to be capable of writing more matter into existence than it erased. This was a deeply uncomfortable thing to propose. Every experiment ever conducted suggested that the number was, in practice, perfectly stable. Protons did not decay. Matter did not appear from nowhere on a laboratory bench. And yet, for us to be here at all, that stability had to fail. Just once. Just barely. In conditions no laboratory could ever reproduce. The second condition Sakharov already held in his hand, because Cronin and Fitch had handed it to him. The laws of physics had to treat matter and antimatter differently. Charge symmetry alone was not enough. The deeper combined symmetry, the one that pairs a particle with its mirrored antiparticle, had to break as well. This was precisely what the kaons had revealed. So the second ingredient was not a guess. It was already sitting in the data, confirmed, undeniable, waiting for someone to recognize what it was for. The third condition was the most subtle, and in some ways the most beautiful. The universe had to be out of balance with itself. It had to be changing, expanding, cooling, falling away from the smooth equilibrium in which every process is perfectly undone by its reverse. In a universe sitting at rest, in flawless thermal balance, any surplus created in one moment would be quietly destroyed in the next. The forward reaction and the backward reaction would cancel, exactly, forever. Only a universe in motion, a universe racing away from its own beginning, could lock in a difference before it had the chance to erase itself. Existence, in other words, required time. It required a universe that was going somewhere and could not return. Consider what this means. 3 conditions, drawn not from philosophy but from the cold logic of particle physics, had to be satisfied at the same moment for any matter to survive. Break the ledger of matter, break the mirror, break the balance. Satisfy all 3, and a universe of pure symmetry could tilt ever so slightly toward being rather than nothing. Fail any one of them, and the great annihilation would have been total. Every particle would have found its partner. Every collision would have ended in a flash of light. The cosmos would have cooled into an endless, featureless sea of radiation, expanding into the dark, containing no stars, no planets, no chemistry, no observers to wonder why it was so empty. Picture that failed universe for a moment. If the annihilation had been complete, if not a single particle had been left over, the cosmos would still exist in a sense. It would still expand. It would still grow colder. But it would be a universe of light and nothing else. A thinning glow stretching across a void that deepens with every passing eon. No atom would ever form. No cloud would ever collapse into a star. No star would ever forge the carbon and the oxygen that make a thinking creature possible. There would be no one inside that universe to notice its perfection, and nothing for them to notice it with. That is the universe the equations describe as the natural outcome. Ours is the exception. We are what was left after the cancellation almost succeeded, and here is the part that should unsettle anyone who follows it closely. Sakharov wrote down the perfect recipe, but the universe, as far as we can measure it, does not seem to contain enough of the second ingredient to make that recipe work. This is the quiet catastrophe at the heart of modern physics. The broken symmetry that Cronin and Fitch discovered is real. It is confirmed. It has been measured again and again across the decades, in kaons, in heavier particles, and most recently, in 2025, in a baryon for the very first time. Yet every time physicists measure how strongly the laws of nature actually favor matter over antimatter, the answer comes back the same. It is too weak. Not slightly too weak, catastrophically too weak. The asymmetry built into the standard model, the entire accepted framework of particle physics, falls short of the matter surplus we observe by many orders of magnitude. The recipe is correct. The kitchen is missing an ingredient we have never found. Think about the size of that gap. The universe preserved roughly 1 extra particle of matter for every billion pairs that annihilated into light. That faint imbalance, 1 part in a billion, is the entire reason for everything you have ever seen or touched. And yet the known sources of broken symmetry, even added together, even pushed to their most generous limits, cannot produce a lien anywhere near that large. They produce something. They do not produce enough. Some other process, some mechanism we have not yet identified, some particle we have not yet detected, must have been at work in the first instance of time, doing what the physics we know cannot. The leading suspect carries a name that sounds almost like poetry: leptogenesis. The idea runs like this. In the earliest moments, long before atoms, long before protons settled into being. The universe may have been populated by neutrinos of enormous mass, particles so heavy that we have never created one and may never directly see one. These hypothetical giants would have decayed, and if they decayed with their own faint preference for matter over antimatter, they would have seeded the young cosmos with a tiny excess of a different quantity, an imbalance among the light ghostly particles called leptons. Then a second process, stranger still, would have stepped in. Unstable twists in the fields of the infant universe, configurations that can exist only at unimaginable temperatures, would have converted that lepton imbalance into the surplus of ordinary matter we are made of. It is an elegant story. It is also for now entirely unconfirmed. The heavy neutrinos it requires have never been observed. The recipe may be right, and the cook may be a particle we have not yet met. This is why the announcement from Geneva in 2025 carried such weight, and why it answered so little. For the first time, physicists had caught matter and antimatter behaving differently in a baryon, in a close cousin of the very particles that build our bodies. The asymmetry they measured was larger than anything ever seen in the lighter particles, and it was still, by an enormous margin, far too small to explain us. The discovery did not close the case. It widened it. It confirmed that the broken symmetry is real, that it reaches into the family of particles we are made of, and that even there, in our own corner of physics, the books still refuse to balance. We can watch the universe leaning. We still cannot find the hand that pushed it. So we are left holding a strange and incomplete certainty. We know that the cosmos is lopsided. We know roughly by how much. We know the three conditions that the lopsidedness required, written down by a quiet man in a country that would soon try to exile his conscience. And we know that the physics in our textbooks cannot, on its own, account for the result. Every atom in your hand is proof that the recipe worked. Nothing in our current understanding fully explains how. Yet even this, the deepest unsolved problem in the story of matter, rests on an assumption we have not yet dared to examine. It assumes there was already something there to tilt. It assumes a universe, a stage, a quantum fire crowded with particles waiting to be sorted into survivors and ghosts. It takes the existence of the players entirely for granted and asks only why one side won. But the harder question, the question hiding beneath the question, is stranger and colder than any imbalance of matter. Before the universe could lean towards something rather than nothing, there had to be a something to lean. And to understand where that something came from, we have to stop staring at the fullness of the early cosmos and turn instead toward the emptiest place imaginable, and discover that it was never truly empty at all. Picture the emptiest place you can imagine. Not the vacuum of a sealed jar with the air pumped out, not the thin, near vacuum between the planets, where a single atom might drift alone for 1,000 years before it meets another. Picture instead a region of space scrubbed perfectly clean, every atom removed, every particle of light carried away, the temperature lowered as close to absolute zero as the laws of physics will ever permit. This is the void as nearly all of us imagine it, a silent, featureless nothing, a stage with no actors, waiting in the dark. That picture is wrong, not slightly wrong, wrong at its very foundation. Ask anyone what a vacuum is, and they will answer without hesitation. It is empty space, the absence of matter, the absence of everything. We learn this as children, and the word itself encourages the error. A vacuum, we are taught, is simply what remains once you have taken everything away. And so we imagine that if we could pull every particle out of a box, what would be left inside is a true and total emptiness. A pocket of pure nothing, held safely behind glass. We treat the void as a container that happens to be unoccupied. The reality is stranger, and it took some of the finest minds of the 20th century to uncover it. The void is not empty. The void can never be empty. Even the emptiest cubic centimeter that the laws of physics allow is not a vacancy, but a medium. It does not rest. It cannot rest. It seethes with a constant, invisible activity that no pump and no refrigerator and no act of removal can ever still. The emptiness, it turns out, is the most crowded thing in the universe. To understand how we learnt this, we have to travel to the Netherlands, to a quiet research laboratory, and a man with a strange and beautiful idea. In 1948, a Dutch physicist named Hendrik Casimir, working in the research laboratories of the Philips company, made a prediction so subtle that it seemed at first almost like a riddle. Take two metal plates, ordinary plates, uncharged, flat, polished, smooth. Place them in a vacuum, parallel to one another, separated by a gap thinner than a hair. According to Casimir, those two plates would feel a force drawing them together. Not because they carried any electric charge, not because of gravity, which at that scale is far too feeble to matter at all. They would be pushed together by the emptiness surrounding them. Consider what this means. There is nothing between the plates. There is nothing outside them. And yet, the nothing pushes. The nothing has pressure. The explanation lies in the true nature of empty space. According to quantum theory, what we call the vacuum is not a still and lifeless void, but a restless sea of fields that fill all of space, and those fields are never perfectly quiet. They flicker, they tremble. Even at the lowest energy a region can possibly have, tiny fluctuations rise and fall without end. Out of these fluctuations, pairs of particles flash briefly into existence and vanish again before they can ever be caught, borrowing energy from the void for an instant and paying it back almost as soon as the debt is made. Physicists call these fleeting visitors virtual particles. They are not a metaphor. They are not a convenient fiction. They are the constant churning froth of the lowest possible state of reality, and they are present everywhere. In this room, in your lungs, in the deepest gulf between the galaxies. Now return to Casimir's two plates. The space outside them is open, and so it can host fluctuations of every size, every wavelength, the long slow ones and the short rapid ones alike. But the narrow gap between the plates is different. It is a confined space, and a confined space can only hold fluctuations that fit. The longest waves are excluded. They cannot squeeze into the gap, and so there are slightly fewer of these flickering disturbances between the plates than there are in the open space beyond them. The result is an imbalance. The restless emptiness presses harder from the outside than from the inside, and that difference, faint but real, shoves the plates together. This is the disturbing reality of the quantum vacuum. The force does not come from the plates. It comes from the difference between two kinds of nothing. One nothing, slightly more crowded, pressing against another nothing, slightly less. For decades, Casimir's prediction lived in the strange borderland between theory and reality, too small to confirm, too elegant to dismiss. The force is almost unimaginably weak at any scale we can feel. To detect it, you must bring two surfaces breathtakingly close, closer than the width of a single bacterium, and you must hold them parallel to a precision that defeats ordinary instruments. The measurement seemed for a long time beyond reach. Then, in 1997, a physicist named Steve Lamoureux, working at Los Alamos National Laboratory, finally pinned it down. Using exquisitely sensitive equipment, he measured the force between two gold-coated surfaces drawn close together in a vacuum, and he found exactly what Casimir had described nearly 50 years before. The pull was there. It matched the theory to within 5%. The emptiness had been weighed, and it was not zero. Let that settle for a moment. A force predicted from the trembling of pure vacuum, derived from the idea that nothing is never truly nothing, was carried out of the realm of pure mathematics and confirmed on a laboratory bench, in our world, with metal and gold and patient hands. This was not a clever thought experiment that happened to be internally consistent. This was a measurement. The void pushes, and we have felt it push. And here is where the comfortable picture of empty space collapses entirely. We began this story imagining the void as a container that happened to be empty. We must now imagine something far harder. The void is not a container at all. It is a substance. It is a thing in its own right, with structure, with energy, with the capacity to exert force on solid matter. When you remove every atom and every photon from a region of space, you have not arrived at nothing. You have arrived at the lowest energy state of the quantum fields, and that state is not silence. It is a faint, eternal hum. This distinction matters enormously, because it changes the meaning of the very question we have been circling from the beginning. We have been asking why there is something rather than nothing, and we have quietly assumed we knew what nothing would mean. We pictured it as an empty stage, dark and still, from which a universe would somehow have to be conjured. But the physics tells us that such a stage may not even be possible. The emptiest emptiness that nature permits is already alive with activity. It already carries energy. It is already, in the only sense that the universe seems to recognize, something. So perhaps the puzzle has been mislabeled from the start. Perhaps the deep mystery is not how something arose out of nothing. Perhaps it is that a true and total nothing, the absolute void of the philosophers, may be a thing that nature simply cannot construct. The vacuum is not the absence we imagined. It is the quietest possible presence. And a quiet presence is a very different beginning than an empty page. This idea reaches further than two plates in a laboratory. The energy hidden in empty space is not confined to the narrow gap between Casimir's metal sheets. If the vacuum carries energy here, then it carries energy everywhere, in every cubic centimeter of the cosmos, stretching across the entire unimaginable volume of the universe. The emptiness between the stars is humming. The emptiness between the galaxies is humming. The vast dark gulfs that make up almost all of reality are not blank at all, but charged with a faint pervasive energy that belongs to space itself, to the stage rather than the players. And in 1998, astronomers found something that suggests this hidden energy is doing real work on the largest scale imaginable. Studying the light of distant exploding stars, they discovered that the expansion of the universe is not slowing down, as everyone had expected, but speeding up. Something is pushing the cosmos apart, gently, relentlessly, against the inward pull of all its gravity. They gave that something a name. They called it dark energy, and by the best measurements we have, it accounts for roughly 68% of everything there is. The single largest ingredient in the universe is not the stars, not the galaxies, not the matter that survived the Great Annihilation. It is the energy of empty space. So the void is not only restless, it may be the dominant force shaping the fate of all that exists. The nothing we feared was lifeless turns out to be the engine of the cosmos. Not the backdrop to the drama, but the most powerful actor in it. This is the turn that should unsettle you, lying there in the dark. We set out to explain a surplus of matter, the one survivor in a billion, and we assumed we understood the empty space it was floating in. We do not. The deeper we look into the vacuum, the less it resembles absence, and the more it resembles a substance we barely comprehend, brimming with an energy we can measure but cannot yet explain. The question of why there is something rather than nothing was always a question about two things: about the something and about the nothing, and we are only now beginning to suspect that we had the second one wrong all along. Consider what this means. We measured that energy at the close of the 20th century, watching distant stars explode across billions of light years, and we found that the expansion of everything was not slowing under the weight of all its matter. It was quickening. Something was pushing the cosmos apart, gently, patiently, from inside the empty space itself. And so physicists set out to do the obvious thing. They tried to calculate how much energy a region of pure vacuum should contain. They reached for quantum field theory, the most precisely tested framework human beings have ever built, a body of mathematics so accurate that in other settings it predicts measurements correct to 10 or more decimal places. They turned that exquisite machinery upon the void, and it gave them an answer. The answer was wrong. Not slightly wrong, not wrong by a factor of 2 or 10 or 1,000. The number that quantum theory predicts for the energy of empty space is larger than the number we actually observe by a factor of 10, followed by 120 zeros. This is the cosmological constant problem, and it is often called the worst prediction in the history of physics. To feel the size of that failure, consider the stacking. It is not the gap between a teaspoon and an ocean. It is not the gap between a single grain of sand and every beach on Earth. It is not the gap between one heartbeat and the entire age of the universe. It is a mismatch so vast that none of those comparisons even begins to reach it. Our finest theory of how empty space behaves looks into the vacuum, calculates its energy, and overshoots reality by a margin the human mind has no shelf to hold. And yet the energy is real. That is the part that should keep you turning it over in the dark. The vacuum energy is not a fantasy or a bookkeeping error. We can read its fingerprints in the accelerating flight of the galaxies. We can feel its quiet cousin in the laboratory, in the faint and stubborn attraction between two uncharged metal plates. The thing is measurable. The thing is there. What we cannot do, not yet, is explain why it carries the modest value it carries, rather than the ruinous value our equations demand. We are in the strange position of a people who can read a single sentence of a language flawlessly and understand nothing whatsoever of the grammar beneath it. If you could somehow drain a sealed box of every atom, every passing photon, every last trace of warmth, and cool it down toward the absolute floor of what is possible, you would not arrive at stillness. You would arrive at a faint and ceaseless seething, a froth of particles flickering into being and vanishing before they can be caught. The physicist Frank Wilczek, who shared the Nobel Prize in Physics in the year 2004 for uncovering how the strong nuclear force binds the heart of every atom, compressed this entire mystery into 3 words. Nothing is unstable. It is a small sentence, almost offhand, and it carries an enormous claim. It says that a true and total void, a nothing with no particles, no stirring fields, no energy at all, is simply not a condition the universe is capable of sustaining. Not because nothingness yearns to become something. Yearning is a human idea, and the vacuum does not yearn. But because the laws of quantum mechanics forbid perfect quiet. They demand fluctuation. They insist that even the emptiest conceivable space must tremble. Sit with that, because it begins to reshape the entire question. We started this long journey assuming that nothing was the natural state and something was the puzzle. That existence was the condition requiring an explanation, and emptiness was the condition that needed none. Wilczek's 3 words turn that assumption completely upside down. If nothing is unstable, then perhaps something is not the anomaly at all. Perhaps something is simply what the universe produces when left to its own rules. Perhaps the genuine miracle, the truly inexplicable outcome, would have been a cosmos that managed to stay empty. But there is a harder objection waiting, and an honest guide does not quietly walk around it. Even if nothingness is unstable, even if the void is compelled to bring forth particles, where did all the energy come from to build a cosmos of galaxies and stars and sleeping bodies? Energy, we are taught from childhood, cannot be created. It can only move and change its shape. To summon an entire universe would seem to require a colossal cosmic loan, a debt beyond any possibility of repayment, a violation of the most sacred rule in all of physics. Here is where the accounting becomes beautiful. When physicists tally the total energy of the universe, they find 2 columns. In one column sits everything we would naturally call positive, the matter, the light, the heat, the locked-up mass of every star. In the other column sits something far easier to forget: gravity. The gravitational pull binding all that matter together carries negative energy. Energy that grows deeper and more negative the more tightly things are drawn together. And when the 2 columns are added, when the positive weight of all that exists is set against the negative depth of all that gravity, the books appear to balance. The grand total comes to something astonishingly close to 0. In a universe that is spatially flat, and the patient measurement of the ancient cosmic light tells us that ours is flat to a remarkable precision. The cancellation may be exact. The sum of absolutely everything may be nothing at all. Consider what that quietly implies. The universe may not be a vast something that had to be paid for. It may be an enormous and intricate arrangement of positives and negatives that, taken together, still adds up to the very nothing we began with. Not nothing in the sense of empty, but nothing in the sense of balanced. A debt and its repayment written across 100 billion galaxies. The Big Bang, by this accounting, did not require an infinite injection of energy from somewhere outside. It required zero. And zero is a number the void can supply. This is the loophole at the center of the pivot. It does not prove that the universe assembled itself. It does not silence the deeper questions. But it removes the most obvious objection of all, the one that insists you simply cannot get a world for free. Apparently, in the strict ledger of energy, you can. The price written on the tag of existence may be exactly zero, and so the matter that became your body, lying here in the dark, is not a thing that was added to the universe at some unaffordable cost. It is one entry in a balance sheet that still totals nothing. And yet a free universe is not an explained universe. The bookkeeping tells us that something from nothing breaks no law of energy. It does not tell us why the laws themselves were standing ready to be obeyed. A balanced ledger still requires a ledger. A fluctuation that gives birth to a cosmos still requires the quantum rules that make fluctuation possible in the first place. We have shown that the vacuum can create without going bankrupt. We have not shown where the vacuum came from, or the mathematics that governs it, or the strange flickering stage upon which the entire performance unfolds. The question simply retreats, and it retreats to the most vertiginous place of all. If something can emerge from a balanced nothing, then we are forced at last to ask about the beginning itself. About the first moment, about whether there even was a first moment, a true edge to time, a boundary beyond which the very word before has nothing left to point at. For if the universe is the books balancing to zero, then we must turn and look directly at the instant the ledger was opened, and it is there, at the very start, that the most formidable minds of the last century went searching for an edge, and found something far stranger than an edge waiting for them. The two men who went looking for that edge were not poets reaching for metaphor. They were among the most disciplined minds the discipline of physics has ever produced, and they expected the beginning to behave like every other beginning they had ever studied. A line has a starting point, a book has a first page, a road has a place where the pavement simply ends and the wilderness begins. Time, they assumed, must be the same. It must have a first instant, a sharp and definite boundary, a wall behind which nothing could be said to exist, because there was no longer any time in which existing could occur. This is the intuition we all carry. It feels not like a theory, but like common sense. In the year 1981, a gathering of cosmologists assembled inside the walls of the Pontifical Academy of Sciences in Vatican City. Among them sat Stephen Hawking, already one of the most consequential theoretical physicists alive, already moving through the world in a wheelchair, already accustomed to thinking in places where ordinary language begins to fail. He had come to present an idea developed with the American physicist James Hartle, and the idea was quietly outrageous. It proposed that the question everyone had been asking about the beginning was not difficult to answer. It proposed that the question was malformed, not unanswerable because we lacked the data, malformed because it pointed at nothing. Consider what this means. For centuries, the deepest version of the puzzle of existence had taken the shape of a temporal question. What happened before the universe? What lit the fuse? What set the first domino leaning toward the second? Every one of those phrasings smuggles in an assumption so deep we never notice we are carrying it. The assumption is that time is a stage that was already standing, empty and waiting, when the universe walked out onto it. Hawking and Hartle proposed to remove the stage. They proposed that time itself was part of the performance, born with everything else, and that there was no dark wing off stage where a before could hide. To make this thinkable, Hawking offered an analogy so clean it has outlived nearly everything else he said in public. Imagine standing at the North Pole of the Earth. You can walk south in any direction you choose. Every road leads away from where you stand. But there is no such thing as walking north from the North Pole. The direction does not run out of road. The direction simply ceases to have meaning. There is nothing broken about the North Pole. No cliff, no edge, no hole in the ground where the planet gives way. It is a perfectly smooth and ordinary point on a perfectly smooth surface. It is only special in this single respect. It is the place beyond which a certain question can no longer be asked. Asking what lies north of it is not hard. It is empty. This is the no-boundary proposal, and the name carries its entire meaning. The beginning of the universe, in this picture, is like the North Pole of time. Trace the history of everything backward, run the cosmos in reverse toward its origin, and you do not arrive at a wall. You do not arrive at a first instant standing in stark relief against an emptiness that preceded it. You arrive instead at a place where time gently loses the quality of being time, where the sharp distinction between a moment and the space around it softens and rounds and finally dissolves. There is no first second, because the very idea of a first second has quietly stopped applying. The beginning is smooth, the beginning is closed, the beginning has no boundary at all, and that absence of a boundary is the whole point. Hawking summarized the audacity of it in a single sentence that reads almost like a riddle. There ought to be something very special about the boundary conditions of the universe, he said. And what can be more special than the condition that there is no boundary? Read that slowly. He was not dodging the question of how the universe began. He was answering it by proposing that the universe is the kind of object that requires no external instruction, no separate launching, no act performed upon it from outside. It contains its own beginning the way a sphere contains its own surface, with nothing left over and nothing hanging off the edge demanding explanation. Now let the weight of that settle, because it is heavier than it first appears. We have spent this entire journey hunting for a cause. We have asked what came before, what triggered the asymmetry, what tipped the balanced books of the vacuum from zero into a cosmos. And here is a serious proposal, advanced by serious physicists, that the hunt has been chasing a question with no referent. Not a question that is hard to answer. A question that, examined closely, turns out to be asking for a place that does not exist, in a direction that does not run. The before we keep reaching for may be the north beyond the North Pole. The hand keeps closing on empty air, not because we are too weak to grasp the answer, but because there is nothing there to grasp. This does not comfort, it disorients. Every fibre of human cognition is built for a world of befores and afters, of causes that precede effects, of stages that stand ready before the actors arrive. We evolved inside the flow of time, fish that have never once been out of the water, and we are now being told that the water itself has a shore where it does not lap against any land, but simply, smoothly, stops being water. The mind reaches for an image and finds none, because every image it can build is already made of time. You cannot picture the absence of a before, because picturing is itself a process that takes a before and an after to occur. And this is where the journey climbs to its most vertiginous altitude. Extend the no-boundary idea across the full sweep of deep time, and the asymmetry we built this entire investigation around begins to look different. Recall the survivor. Recall that for every billion pairs of matter and antimatter forged in the first instance, only a single particle of matter remained when the great annihilation finished its work. We have been treating that survivor as a riddle of cause. Something must have favoured it, something must have tipped the scale. But if the beginning has no boundary, no first moment standing apart from a prior emptiness, then there is no outside vantage from which the scale could have been tipped by anything external at all. The tilt, if it is real, was woven into the closed and seamless fabric of the beginning itself, present in the same way the curvature is present at the North Pole, not added to it from beyond. Hold the smallness of the numbers against the smoothness of this picture, and the dread sharpens. Today the observable universe contains, on average, roughly one atom for every cubic meter of the vast intergalactic dark. Against each of those lonely atoms stand more than 400 photons of cosmic background light per cubic centimeter, the cold afterglow of the annihilation that nearly erased us, still streaming through space at a temperature of 2.725 degrees above absolute zero. That ratio is the ash. It is the record of how thoroughly matter and antimatter destroyed one another. Nearly everything that could exist did not survive. Not most of it, not the overwhelming majority of it. Nearly the entire original population, gone, converted to light, leaving behind a residue so faint that an atom now wanders alone through a volume of space larger than a human body. And every one of those surviving atoms, the proposal suggests, traces back not to a cause that acted upon the universe, but to a beginning that has no behind, no prior, no place where a cause could have stood to act. The survivor is real. You are built from survivors. The carbon in your bones, the iron in your blood, the oxygen filling your lungs as you lie listening to this. Every atom of it is the 1 in a billion remainder of a slaughter that finished before the universe was a single second old. That much is measured. That much is fact. What the no-boundary picture removes is the comfort of being able to ask what made it so, by quietly proposing that the question has no place left to point. There is a particular kind of fear that arrives not from danger, but from the collapse of a category you did not know you were leaning on. We are leaning on before. We have leaned on it through every paragraph of this descent, the way a climber leans on a handhold without ever looking down to check that the rock is solid. The no-boundary proposal invites us to look down. It invites us to notice that the handhold of before, the bedrock assumption beneath every origin story humanity has ever told, may not extend all the way to the bottom. It may simply round off an end, smooth and seamless and without edge, somewhere in the first vanishing fraction of the first instant, where the word before runs out of world to describe. But an idea this strange does not pass into physics unchallenged. A picture that dissolves the beginning rather than explaining it was always going to provoke a reckoning, and the reckoning came, decades later, from minds every bit as formidable as the ones that first drew the seamless edge. For if Hawking and Hartle had truly closed the books on the question of the beginning, the equations themselves would have to agree, and when a new generation returned to those equations with sharper mathematical tools, what they found was not agreement. What they found was a fight. The fight began in the year 2017. A physicist named Neil Turok, working at the Perimeter Institute for Theoretical Physics in Waterloo, Canada, returned to the seamless edge alongside two collaborators, Job Feldbrugger and Jean-Luc Linus. They did not arrive with philosophy. They arrived with new mathematical techniques, sharper methods for handling the enormous sum that sits at the heart of the no-boundary proposal. That sum is a strange and beautiful thing. To calculate the probability of our universe, you cannot simply trace one history backward. You have to add together every possible history at once, every conceivable shape the infant cosmos could have taken on its way to here. Hawking and Hartle believed that when you performed this sum correctly, the smooth, rounded, edgeless universe would emerge as the most likely outcome. Turok and his colleagues performed the sum with their new tools and watched it come apart in their hands. What came back was not a refinement, it was a collapse. The careful addition that was supposed to deliver an orderly cosmos instead refused to settle, refused to point toward a universe anything like the calm one we inhabit. In Turok's unsparing phrase, the proposal had just failed miserably, not in some small technical corner, not in a detail that a later patch might quietly repair. The failure, as he described it, reached the foundation. The seamless edge, examined under brighter mathematical light, seemed to dissolve into something that could not hold a stable world together at all. This is the disturbing texture of the deepest questions in physics. The closer you look, the less solid the ground becomes. the response from the other side was not surrender. Thomas Hertog, who had collaborated with Stephen Hawking for 20 years, joined with Jonathan Halliwell of Imperial College in London to mount a vigorous defence of the original idea. They argued that Turok and his colleagues had made the wrong choices at the very start, that the new methods rested on assumptions the no-boundary proposal had never accepted. The disagreement, both sides came to recognise, was not really about arithmetic. Either camp could check the other's numbers. The fight was about something far more unsettling. It was a disagreement about how nature actually works at the level where mathematics meets reality, about which assumptions are permitted when you try to write down the birth of everything. Consider what this means. Two groups of brilliant physicists, staring at the same equations, reach opposite conclusions about whether the universe could have begun without a beginning. The numbers do not decide it. The numbers are agreed upon. What separates them is a choice so deep that it lies beneath the mathematics, in the silent assumptions each side makes about what is real and what is merely a useful fiction. This is not a flaw in the scientists. It is the shape of the cliff face itself. We have climbed to a height where the handholds are no longer carved from observation, but from intuition about a domain no experiment has ever touched. The no-boundary proposal was never the only path up this wall. While Hawking and Hartle were drawing their edgeless universe in the early 1980s, two other physicists were sketching a rival route. Alexander Vilenkin, working at Tufts University in Massachusetts, and Andrei Linde, working independently, proposed something even stranger than an edge that rounds away. They proposed that the universe tunneled into existence, not from a previous universe, not from a seed of space waiting in some larger arena, from a state of no space and no time at all. They borrowed the idea from the quantum world, where a particle trapped behind a barrier it does not have the energy to cross can simply appear on the other side, as though the wall were a suggestion rather than a law. In their picture, the entire cosmos performed that same impossible passage, tunneling out of absolute nothing and into being. This tunneling model is mathematically distinct from the no-boundary proposal. It is not a rephrasing of the same idea in different words. It is a separate hypothesis, with its own equations and its own predictions, and the two have remained in quiet competition for more than 4 decades. Neither has won. Neither has been ruled out. Both describe a beginning that is not a beginning in any sense your daily life would recognize. A transition from nothing to something that obeys no rule you have ever watched operate. Here is the truth that everyday experience works tirelessly to hide from you. In the world you can see and touch, nothing comes from nothing. A fire needs fuel. A sound needs a source. A child has parents, and those parents had parents, and the chain runs backward without a single broken link as far as you care to follow it. Your entire intuition about cause and effect was built inside a universe that already existed, by a brain that evolved to track rocks and predators and seasons. That intuition has no jurisdiction at the edge of time. It was never tested there. It was never meant to reach there. When physicists speak of the universe tunneling from nothing, they are describing an event for which your every instinct is not merely inadequate, but actively misleading. The word nothing itself begins to fracture the longer you hold it. The nothing these theories invoke is not the nothing you picture, not the emptiness of the dark sky between the stars, not the emptiness of the deep space between the galaxies, where a single atom may drift alone in a cubic meter of void. Not even the emptiness of a sealed chamber pumped free of every last particle. A nothing deeper than all of these, a nothing without space to be empty, and without time in which to be anything at all. Try to hold that in your mind, and you will feel it slip. There is nowhere for your imagination to stand. There is no room, because room itself is one of the things that does not yet exist. Now extend that across deep time, and the vertigo only sharpens. The matter that survived the Great Annihilation, the single particles spared from every billion, was forged in a universe that may itself have had no first moment, no edge, no outside. Every atom in your body traces its lineage back not to a clean beginning, but to a question physicists are still fighting over. an origin that dissolves into mathematics the instant you press on it. You are made of the survivors of one catastrophe, born from a cosmos whose own birth refuses to resolve into a single coherent story. The ground beneath the ground beneath the ground gives way, and yet the theories keep coming. The fight between Chirok and Hertog, the rivalry between the rounded edge and the quantum tunnel, are not signs that physics has given up. They are signs that physics has walked further into this strange country than any human thought it could go, and is still walking, still drawing maps of a place where the words before and outside and nothing lose their meaning one by one. Each model is an attempt to say the unsayable in the only language precise enough to try. The language of equations. Each one reaches toward the same impossible target from a different angle. One question waits at the center of all of them, patient and unanswered, growing larger the closer we approach. If the universe truly came from nothing, then what, exactly, do we mean by that final word? That final word is exactly where a physicist named Lawrence Krauss decided to make his stand. In the year 2012, he published a book whose title read almost like a dare. He called it A Universe from Nothing. The argument inside was as bold as the cover promised. Krauss had spent decades studying the empty space we have been circling for the past hour. The vacuum that is not a vacuum. The void that hums and trembles with particles flickering in and out of existence. And he had arrived at a conclusion he believed could dissolve the oldest question in all of philosophy. Nothing, he argued, was never stable to begin with. Consider what this means. The quantum vacuum is not a passive emptiness patiently waiting to be filled. It is a restless, seething medium in which pairs of particles appear and vanish without pause, borrowing energy from the universe and repaying it before the cosmos can register the debt. Given that ceaseless background activity, Krauss reasoned, the sudden appearance of a universe is not a miracle requiring some divine accountant to balance the ledger. It is something far closer to an expectation. Empty space does not stay empty. The void cannot hold its breath forever. A universe, in this picture, is simply what nothing does when it is left entirely alone. This is the strange and quietly hopeful reality that the quantum vacuum offers. For 400 years the question had felt like a wall, a place where every chain of explanation ran out of road. Why is there something rather than nothing? The phrasing assumes that nothing is the natural state, the default, the resting position the universe should occupy, unless some force intervenes. Krauss turned that assumption upside down. Nothing is not the default. Nothing is the one configuration the laws of physics will not permit to last. The Nobel laureate Frank Wilczek compressed the entire argument into 3 words that fit on a single breath. Nothing is unstable. A true and total void, a perfect static emptiness, is forbidden by quantum mechanics in the same way that a pencil cannot be balanced forever on its sharpened tip. The fluctuations must come. And once they come, something is here. To appreciate how comforting this idea is meant to feel, consider the alternative it claims to replace. For most of human history, the existence of the world demanded an external reason, a first cause standing outside the world to push it into being. Leibniz reached that conclusion at his writing desk 3 centuries ago, and he gave the cause a name. Krauss believed he could remove the need for that external push entirely. The universe could be its own explanation. The laws of quantum mechanics, applied to empty space, would generate existence on their own, with no hand required to start the engine. It is a vision in which the cosmos lifts itself into being by its own internal rules, the way a river carves its own valley simply by flowing. For a moment, standing inside that vision, the wall seems to dissolve. The question seems answered. But the answer has a limitation, and the limitation is profound. The book provoked a response that has never quite faded, and it came not from another physicist, but from a philosopher named David Albert, a man trained in quantum theory before he turned to the philosophy of physics. Albert read the book and raised a single objection so simple that it has proven almost impossible to escape. The nothing in Krauss's title, he pointed out, is not actually nothing. It is the quantum vacuum. And the quantum vacuum is a something. It is a physical system with definite properties, a medium that obeys equations, a stage governed by the laws of quantum mechanics. To say that this vacuum gives birth to particles is a remarkable scientific achievement. But it does not answer the question that Leibniz asked. It answers a different, smaller question, and quietly hopes you will not notice the substitution. This distinction matters enormously, because it cuts to the heart of what the word nothing was ever meant to carry. When the philosophers asked why there is something rather than nothing, they did not mean why is there something rather than empty space. They meant something far more radical. Why is there anything at all, including the empty space, including the quantum fields that fill it, including the very laws that tell those fields how to behave? Krauss had explained how a universe of particles could emerge from a vacuum. He had not explained where the vacuum came from, nor where its laws came from, nor why those particular laws hold rather than some other set, nor why there is any lawfulness in the first place. The achievement was real. But it was not the answer to the question, not because the mathematics failed him, but because the word itself had quietly changed shape in his hands. So the wall returns, having moved. This is the recurring pattern of the entire investigation, and by now you can feel its rhythm in your bones. Every time physics reaches toward the bottom drops one level deeper. We explain the matter around us as the survivor of a 1,000,000,000 annihilation. Then we asked why there was a surplus to survive, and the answer pointed to a delicate asymmetry in the laws themselves. We explained the appearance of a universe as the instability of the vacuum. Then we asked where the vacuum and its laws came from, and the floor opened again. Each explanation is genuine. Each one is also a relocation. We do not reach the ground. We discover that what we took for the ground was a ceiling, with another room beneath it, and another beneath that. Not an answer, but a forwarding address for the question. And the laws themselves, the very rules that Krauss leaned on, carry a wound that no one has been able to close. We met it earlier, but it belongs here too, at the final layer, because it is the clearest evidence that our deepest theory of the vacuum is missing something enormous. When physicists use quantum field theory to calculate how much energy should be stored in empty space, the theory returns a number. When astronomers measure how much energy is actually stored in empty space, by watching the expansion of the cosmos, they find a vastly smaller number. The two do not disagree by a little. The prediction is larger than the measurement by a factor of 10, followed by 120 zeros. It is the single worst prediction in the history of physics, a mismatch so total that calling it an error feels almost generous. The energy of empty space is real. It is measurable. And our finest theory of what empty space is gets its value wrong by a margin that has no rival anywhere in science. Sit with the strangeness of that for a moment. The thing Krauss called nothing, the humming vacuum he asked to give birth to the universe, is a thing we do not understand at the most basic level. We cannot calculate its energy. We cannot derive its laws from anything deeper. We can only measure what it does and stand puzzled before the gap between our measurement and our mathematics. To say the universe came from this vacuum is, in one honest sense, to say the universe came from a mystery we have merely learnt to describe with greater precision. The void is not the bedrock of the explanation. The void is the largest unsolved problem we have. And yet, against all of this, there is a thread of genuine hope, thin but real, and it is the newest thing in this entire story. It comes from the place we visited near the beginning, the place where matter first outran antimatter by a single part in a billion. For 60 years, every confirmed observation of the universe playing favourites between matter and its mirror image had come from one narrow family of particles, the mesons, the fleeting pairings of a quark and an antiquark. Mesons are not what you are made of. The protons and neutrons in your body belong to a different family, the baryons. And in all those decades, the baryons had never once been caught breaking the symmetry. The visible universe is built from baryons, and the visible universe had kept its secret. Then, in March of 2025, that silence finally broke. The collaboration at the largest machine humanity has ever built announced that they had watched a baryon behave differently from its antimatter twin. For the first time, the particles that compose stars and planets and the cells of every living thing had been caught doing exactly what the survival of the universe requires them to do. They had treated matter and antimatter as not quite equal. It is a tiny effect, smaller than a hair on the scale of the problem it must one day solve, far too small on its own to account for the great surplus that let you exist. But it is the first crack in a wall that had stood unbroken for 2 generations. It is the first time the right family of particles has shown the right kind of imbalance, and it points beyond our current theory, toward physics we have not yet written down, towards some deeper law that might at last explain the full 1 in a billion margin between being and oblivion. Here, then, is where the science leaves us, balanced on a knife's edge between 2 feelings at once. On one side stands the hope. The vacuum is unstable, existence may be its natural overflow, and a new crack has opened in the wall that might finally lead somewhere. On the other side stands the dread that no measurement has been able to lift. Every explanation moves the question rather than ending it. The word nothing keeps dissolving the moment we try to hold it. The laws we lean on hide a flaw the size of the cosmos. We have walked as far as instruments and equations can carry us, and the ground beneath that furthest step is still not solid. Which means the question that began this journey is still standing, exactly where Leibniz left it, waiting in the only room large enough to hold it. Before we step into that room, there is one more idea to lay down on the table. One final candidate that physicists have built, precisely because the answers we already have keep falling short. It is called leptogenesis. The name is heavy, but the picture it paints is almost simple. In the first unimaginable instant of the universe, the theory proposes, there existed particles we have never seen, very heavy cousins of the ordinary neutrino, so massive that no machine we have ever built has produced a single one, born in the fire and gone almost as quickly as they came. These heavy neutrinos did not decay evenly. Like the kaons, like the lambda baryon, they preferred one path over its mirror, spilling out slightly more of one kind of particle than its opposite. Not by much, by the faintest statistical lean. But a lean is all the universe has ever needed. That faint lean produced an imbalance, not in matter directly, but in a quantity physicists call lepton number, the running tally of light particles like electrons and neutrinos. Here the story takes a turn that sounds almost like mythology. In the searing heat of the young cosmos, before the forces of nature had fully separated, there moved through space a kind of process with a strange and beautiful name. Physicists call them sphalerons. They are not particles. They are knots in the fabric of the fields themselves, fleeting configurations that can form only when the universe is hot enough, and they have the power to do something forbidden in our cold modern world. They can convert one kind of imbalance into another. They took the lepton asymmetry left behind by the heavy neutrinos and rewrote part of it as a baryon asymmetry, a surplus of the very protons and neutrons that would one day become stars, planets, and the cells reading these words. This is the hope, stated in its most concrete form. Not a vague gesture toward unknown physics, but a specific machine, a sequence of steps that satisfies every one of Sakharov's 3 conditions at once. The heavy neutrinos break the symmetry between matter and antimatter. The sphalerons violate the conservation of baryon number. The expansion of the cooling universe drags everything out of balance. On paper, the recipe is complete. On paper, the one survivor in a billion is no longer a miracle but a consequence. And then the dread returns, quiet as always, riding in on the back of a single word. Undetected. The heavy neutrinos at the heart of leptogenesis have never been observed, not glimpsed in a collider, not inferred from a decay, not caught in any detector buried in any mountain or sunk beneath any sea. They are required by the theory and absent from the world. The mechanism is elegant precisely because it explains what we see, and it is fragile precisely because it rests on particles that may lie forever beyond our reach. We have written down a beautiful answer to the oldest question in physics, and we cannot yet tell whether nature ever read it. So consider where this leaves the whole long argument. We began with a number, the one survivor in a billion, your atoms and mine standing as the only evidence that the books did not perfectly balance. We followed that number backward through Dirac's equation and Anderson's cloud chamber, through the kaons at Brookhaven and the lambda baryon at CERN, through the trembling plates of the Casimir vacuum and the silent floor hidden inside the cosmological constant. Every step brought a real measurement, a verified fact, a piece of solid ground, yet every step also widened the gap between what we can describe and what we can explain. This is the strange shape of the deepest physics. It does not run out of answers, it runs out of certainty. The closer we look at the origin of something, the more the word nothing slips through our fingers, until it stops behaving like an absence and starts behaving like a presence with rules of its own, a nothing that fluctuates, a nothing that cannot hold still, a nothing that, given the laws we have measured, was perhaps never an option at all. Yet to say the laws forbid a true void only moves the mystery one step deeper, into a question no instrument has ever been built to answer. Where did the laws come from? Why these laws, and not some other set? Why any laws at all? That is the wall the science finally meets. Not a wall of ignorance about particles or forces or fields, those we will keep chipping away at for centuries, but a wall around the rules themselves. We can explain the matter using the laws. We cannot yet explain the laws using anything deeper. The quantum vacuum may hand us a universe for free, its books balanced to zero, its overflow inevitable, yet the vacuum arrives already equipped with the machinery to do so, and that machinery is the very thing we set out to account for in the first place. There is a temptation, here at the edge, to call this a defeat. It is not. To know exactly where understanding stops is itself a profound kind of understanding. We have mapped the territory all the way to its border. We have named the heavy neutrinos we cannot find, measured the asymmetry we cannot fully explain, and weighed the vacuum whose energy we cannot predict. We have done the astonishing work of carrying a question first whispered at a writing desk in the 17th century all the way to the colliders and telescopes of our own age, and we have placed it, intact, exactly, one step beyond our grasp. The physics has done everything physics can do. It has taken the question as far as equations reach, and then handed it gently to something older than equations. Because the moment we stop asking how the universe arranged its matter, and start asking why there is a universe to arrange anything at all, we have already crossed a border. We have stepped out of the laboratory and into a far stranger room, one whose walls are not built from evidence but from thought itself. The instruments fall silent there, the numbers lose their grip, and the only tools that still function are the ones the philosophers carried with them 3 centuries ago, when they first dared to ask the question we have spent this entire journey trying, and failing, to leave behind. Step fully into that room now. It has no dials, no readouts glowing in the dark, no antenna humming on a distant hillside. It is older than every laboratory ever built, older than the first telescope, older even than the first written word. And it holds only one piece of furniture, the question itself, resting in the center of the floor exactly where Gottfried Wilhelm Leibniz set it down on his writing desk in 1714. Why is there something rather than nothing? He laid it there gently, and for 3 centuries, no one has managed to lift it and carry it back out. What we can do, here at the end, is sit with it. Not to solve it. The whole journey has shown us that solving it may not be the kind of thing this question permits, but to hold it up to the light for a moment, and to notice that the 2 oldest answers humanity has ever offered still stand facing each other across that floor, neither one defeated, neither one able to land the final blow. Perhaps nothingness was never truly an option. This is the first answer, and it is strangely hopeful. Jean-Paul Sartre, writing in the vocabulary of philosophy rather than physics, proposed that perfect nothingness would annihilate itself, that even absolute non-being contains a flaw it cannot survive, a quiet self-negation built into its very emptiness. Centuries later, and an entire discipline away, Frank Wilczek arrived at the same intuition by a completely different road. Wilczek won the Nobel Prize in Physics in 2004 for uncovering how the strong nuclear force binds the heart of every atom, and he compressed the whole idea into 3 words. Nothing is unstable. Not unlikely. Not improbable. Unstable, in the way a pencil balanced on its sharpened point is unstable, certain to fall, certain to become something the instant it is left alone. If that view is correct, then existence was never the surprise. The surprise would have been its absence. A true and permanent void, on this reading, is not the natural state that something had to fight its way out of. It is a state so fragile that it could not last even for an instant, because the same quantum restlessness that drew 2 metal plates together in Hendrik Casimir's vacuum in 1948 would have stirred within the nothing and broken it open. On this view, you are not a miracle that defied impossible odds. You are what happens when nothing tries and fails to remain nothing. Or perhaps the universe owes us no reason at all. This is the second answer, and it is colder. Bertrand Russell gave it its plainest form in 1948, in a famous broadcast debate when he refused the demand for a cause and simply said that the universe is just there, and that is all. The physicist Sean Carroll carries that same position into our own century. The universe simply is, he argues, without ultimate cause or explanation, and the hunger we feel for a deeper reason may be a hunger the cosmos was never obligated to satisfy. On this view, there is no hidden engine beneath existence, no metaphysical flaw under the floor. There is only the brute, silent fact that something is here, and the demand for a why is a habit of the human mind, not a property of the world. These 2 answers do not merely disagree about the solution. They disagree about whether the question is even legitimate, and that is what makes the room they share so strange. Leibniz himself stood firmly with the first camp, though he reached it on foot, by reason alone, 200 years before anyone measured a vacuum or split an atom. He could not accept that the universe was simply there. To him, every fact demanded a sufficient reason, an explanation for why it was this way and not some other way. And a universe that existed for no reason at all struck him as a debt left permanently unpaid. So he followed the chain of reasons backward, each thing explained by the thing before it, until he reasoned his way to something that needed no further explanation, a necessary being, existing not by accident but by its own nature. That was his answer. Not a proof in the modern sense, but a refusal to let the question go unanswered, even if the only answer he could build was one that could never be tested. 3 centuries later, we have instruments Leibniz could not have dreamed of, and we have arrived at almost exactly the same fork in the road. We can measure the energy of empty space with extraordinary precision and find it real. We can count the survivors of the Great Annihilation, 1 lonely particle of matter for every billion pairs that destroyed each other, and we can confirm that ratio against the oldest light in the sky to within a single %. We can watch a lambda baryon in the tunnels beneath the French and Swiss countryside betray the faintest preference for matter over antimatter, a result so new it reached the world only in March of 2025. We have learned, in other words, almost everything about how the something behaves, and we stand exactly where Leibniz stood on the question of why there is any something to behave at all. This is the honest shape of where we have come. The physics has narrowed the question without closing it. It has stripped away the easy answers, the comfortable misconceptions, the idea that empty space is truly empty, or that nothing is truly nothing, or that the laws themselves require no explanation. Every layer we peeled back revealed another beneath it, and at the bottom, where we expected to find bedrock, we found instead the same question we started with, polished now by 300 years of failure, but undiminished. So what are you supposed to do with a question that the finest minds and the finest machines have carried to the very edge of knowledge and no further? This is the part no telescope can do for you. These questions have no universal answer. Different people, standing in this same room, will reach out and touch the question and feel entirely different things. Some will feel the cold of Russell's brute fact and find in it a kind of freedom, a release from the need to justify their own existence to anyone or anything. The universe is just there. You are just here, and there is nothing you are required to earn. Others will feel the pull of Leibniz and Sartre and Wilczek, the sense that the something is not an accident but an inevitability, that the void itself was always going to tip over into being, and that you are therefore not an intruder in the cosmos, but its natural and unavoidable consequence. Both responses are available to you. Both have been held by people far wiser than the question's loudest opponents would admit. And the universe, indifferent as it is, will not correct you whichever one you choose, because the universe has not told us, and may never tell us, which one is true. There is a third response, quieter than the other two, and it may be the most honest of them all. Ludwig Wittgenstein, in his Tractatus, drew a careful line around what language could say, and then pointed past it. The mystery, he suggested, is not how the world is, but that it is. Existence itself, not its arrangement, was for him the thing that could be felt but never spoken, the place where the words run out and only wonder remains. He called it the mystical. Martin Heidegger, lecturing at the University of Freiburg in 1929, gave the same astonishment a grander title and named it the fundamental question of metaphysics, why there are beings at all, and not rather nothing. Neither man pretended to answer it. They did something rarer. They insisted that we keep feeling the strangeness of it, that we never let the question grow so familiar that it stops astonishing us. Notice what has quietly happened over the course of this long night. We began with a number, the harshest and most specific number in all of cosmology, one extra particle of matter for every billion that annihilated. We followed it down through the microseconds after the beginning, through Paul Dirac's equation and Carl Anderson's accidental photograph, through the kaons that broke symmetry at Brookhaven, and the baryons that broke it again 60 years later. We followed it into the vacuum, into Casimir's plates and the worst prediction in the history of physics, the gap of a number with 120 zeros between what our theories expect of empty space and what we actually measure. And the whole descent has carried us, step by patient step, away from arithmetic, and towards something that arithmetic was never built to reach. Consider what that means for the place you occupy tonight. You are not standing outside the universe, examining it through glass. You are made of the very surplus you have been asking about. Every atom in your hands and your eyes, and the quiet machinery of your beating heart drawn from that one in a billion remainder, assembled out of the only matter the early cosmos allowed to survive. The question is not something you are looking at. It is something you are. You are the universe's leftover, grown complicated enough to wonder why it was left over at all. And the stage on which you wonder is almost unimaginably empty. Between the galaxies, space thins to roughly a single atom in every cubic meter. A solitude so complete that the richest cup of intergalactic vacuum holds less substance than the most perfect emptiness any laboratory on Earth has ever achieved. Through that emptiness drifts the faint afterglow of the beginning, around 411 particles of ancient light in every cubic centimeter, cooled now to a whisper just under 3 degrees above absolute zero. The something we have been chasing is, by overwhelming measure, almost nothing. A scattering of survivors in an ocean of cold and patient dark, and even the emptiness is not idle. The vacuum that Casimir proved could press 2 metal plates together is the same vacuum that, across the largest scales we can survey, is quietly pushing the entire cosmos apart. Roughly 68% of everything, of all the energy there is, appears to be this energy of empty space, revealed in 1998 when astronomers tracking distant exploding stars realized the expansion of the universe was not slowing down but speeding up. The nothing has a weight. The nothing has a pressure. The nothing, it turns out, is the dominant feature of the something, the largest single ingredient in the entire recipe of existence. And we cannot explain its value, cannot derive it, cannot say why it is small rather than enormous, or present rather than absent. This is the room you are sitting in, not the warm and finished cosmos of the storybooks, but a vast, cold, mostly empty expanse, governed by an energy we cannot account for, populated by the rare survivors of an ancient annihilation, and threaded through at its very foundation by a question that 3 centuries of genius has sharpened, but never resolved. Perhaps the question itself is the answer. Perhaps existence requires no reason beyond the bare fact of its occurrence, and the universe simply is, without cause, without author, without the deeper why that Leibniz believed must lie beneath everything. The physicist Sean Carroll holds exactly this view. The cosmos is a brute fact, complete in itself, owing no explanation to anyone. Bertrand Russell said it more plainly still. In 1948, the universe is just there, and that is all. Or perhaps the opposite is true. Perhaps, as Jean-Paul Sartre suggested, perfect nothingness would unravel itself, would annihilate its own emptiness, so that a pure and stable void was never an option in the first place. Not a void that happened to fill, a void that could not remain a void. We do not know which of these is right. We may never know. These questions have no settled answer, and they may have no answer that a human mind, itself a temporary arrangement of the surviving matter, is built to hold. Different people, standing under the same dark sky, will reach different conclusions, and none of them can be proven, and none of them can be wholly dismissed. The choice of what to believe in the silence belongs to you. It always has. Consider where you actually are. Across the great gulfs between the galaxies, space holds on average a single atom in each cubic meter, a thinness past all imagining, while through that same emptiness drift the cold remnants of the first light, roughly 411 photons in every cubic centimeter, glowing faint and even at 2.725 Kelvin, the last warmth of a fire that went out almost 14 billion years ago. You are a knot of heat in all that cold. Every atom inside you is a survivor of an annihilation that erased nearly everything, sparing only one particle in 10 billion, and somehow assembled the leftover into a creature that can ask why it was spared at all. That is not a small thing. It is perhaps the least small thing there is. The universe did not have to permit observers. It did not have to leave a remainder. It did not have to round at the very first instant in favor of being. And yet it did. And here you are, awake inside the surplus, holding a question older than every language, turning it slowly in the quiet. Nothing should be here. And yet you are, the rarest of survivors, reading the universe